you very much for the invitation. So today I want to talk to you about video pre-training, or VPT, where we're going to try to learn to act by watching unlabeled videos from the internet. And this was done with this fantastic team of people that were in my team at OpenAI, and I want to give them huge amounts of credit for all the hard work that they did. This paper was at NeurIPS this year. So in hard reinforcement learning domains, arguably the biggest Achilles heel is exploration. Many algorithms do not know how to learn to do anything, or at least the next thing, because of the exploration bottleneck. So an approach that we've tried for decades is intrinsic motivation, where you try to encourage algorithms to go to new states, and that works okay. So there was this kind of grand challenge game for many years in the field in Atari called Montezuma's Revenge, and most algorithms that basically had no intrinsic motivation got a score of 0. And if you did intrinsic motivation, you got a couple thousand points, and there was a lot of fanfare in 2018 for this algorithm that got over 11,000 points. Last year, we had a paper in Nature on an algorithm called Go Explore that really works quite well on these hard exploration challenges. And it gets basically arbitrarily high points and solves this game. It beats the human world record and gets, sometimes 18 million points on this game. It solved all of the unsolved Atari games at the time, and also solved really kind of hard exploration robotics challenges in simulation. For example, here the robot gets no reward unless it puts away one of its toys. And you can see that Go Explore in blue solves a task every time, and intrinsically motivated PPO almost never solves the task. So if you want intelligent exploration, intrinsic motivation doesn't really work that well. Go Explore, I think, works quite well and is very promising, but it's kind of a complex manually designed algorithm. It hasn't yet been proven in rich 3D worlds like Minecraft, for example. And I'm kind of somebody who believes in, lots of compute, kind of like a simple solution. And so I think there's a question, which is there another way to be solving this challenge of really hard exploration? And to borrow from Isaac Newton, AI sees further by standing on the shoulders of giant human data sets. I think that's the lesson of the last few years with things like GPT, Clip, DALL-E, AlphaStar, etc. And the internet is full of tutorials of how to do hard things. For example, learn how to use Photoshop or Gmail or play Minecraft, or even do things like assemble IKEA furniture. And so the question we had with this project is, could we basically harness the GPT Playbook, but for embodied virtual agents to learn really hard things? And so we're basically going to first pre-train on noisy internet scale data. Then we're going to fine tune with RL, and of course, profit. So our hypothesis here is that pre-training should give us what we call a behavioral prior that allows learning tasks that are otherwise effectively unlearnable. So if you think about it, normal exploration is exceedingly dumb. It basically just takes random actions every once in a while, or samples from the action distribution. A behavioral prior learned from pre-training, which is what VPT gives you, instead says, in any situation, if I don't know what to do, just do what humans would do in this situation. And we think that's a much better solution. So the domain that we chose here is Minecraft. We did that because it's a hard exploration domain. It's very open-ended, and I'm very interested in open-ended learning and open-ended algorithms. It's got huge amounts of data from the internet. But I also want to emphasize this is a very generic method that has nothing to do with Minecraft. We just tested it here. For example, you could use this method to learn how to do anything on your computer. So we specifically, for that reason, chose the most general observation and action space, which is the one that humans use. So we're going to go from pixels directly to mouse movements, the keyboard presses, and act at a very high frequency. And that gets us a lot of properties. One is it means that every time you want to apply VPT to a new domain, you don't have to specifically manually design and debug a new action space. It's also lossless, which means we can model everything a human can do. If we see a human doing it, we should be able to do it. And also, it's just really pushing the limits of our algorithms, because it means that we're not simplifying the domain specifically for RL. We're really trying to learn to do what humans can do, which is one of the goals of AGI research. All right. The challenge with this approach is that videos on the internet are unlabeled. So unlike for text, music, and image, you don't get the next bit of label for free. So, in text, you get the next word, in music, the next note, and in images, the next pixel. But in a video of somebody doing something on the internet, you don't know what actions they're taking that produce that video. for example, in Minecraft, if they, what buttons they're pressing and how they're moving their mouse. So to solve that problem, we train an inverse dynamics model, or IDM, which just learns to predict the action that must have been taken at every time step, given the past and the future. And that's actually a pretty easy problem. For example, if you saw this little video here, you could tell that the agent must have pressed the jump button just by looking at the past and the future. So that gives us this IDM over here, and that allows us to go and label online videos once we train that. And then we can just do behavioral cloning at scale in the GPT sense. So you go from past video to the next action that should be taken, train out a whole bunch of data. We ended up using 70,000 hours of data. And then you can auto-regressively roll this thing out in a simulator by just doing next action, next action, next action. So we here trained a 500 million parameter transformer and ResNet to do that. All right, so one important hypothesis underlying this work is that, if you have a limited amount of data, then basically an IDM is an easier thing to train than a behavioral cloning model. So behavioral cloning is really, really hard, and that's why you'd expect it to be data hungry. It has to predict the next action from the past only. So in a situation like the one you see here on the left, it has to figure out, is the human going to build a house or a farm, for example? That means that the model has to model what humans' intent is, but also how to accomplish those very, very difficult tasks. An IDM, in contrast, gets to see the past and the future. All it needs to really understand is the physics of the game, which usually are general and apply everywhere in the game, which is, for example, that the jump button makes the character fly up in the air. All right, so the high-level view of our method here, you're going to collect internet data. We got about 70,000 hours. You then train the inverse dynamics model, which, to do that, we paid contractors up to play Minecraft for about 2,000 hours. And there we're recording the actions they're taking while they're playing it. Those are the labeled data we give to the IDM to train it. And it then learns, oh, given this past and future, this is the action that was taken. That then allows us to label all of the unlabeled videos we got from the internet, and then we can behavioral clone at scale. So here we can now look at the answer to the question of whether the IDM is easier than the behavioral cloning model to train. And you can see loss curves here. So, lower is better. And immediately, even at very low data, the BC is already worse off. And then look at the scaling laws. As you add orders of magnitude more data, you can learn the BC task, but its learning is shallow. It's very hard to learn. Whereas the IDM kind of quickly saturates and performs very well. And you basically are seeing roughly a 2 order of magnitude difference. So it would be far better to solve this problem, the IDM problem, take that solution and then go get the data that you need to solve the much harder BC problem than directly try to go get the BC data. And here's a shot of performance of the IDM on key presses and mouse movements. And you can see that after you get like the 2,000 hours, you actually get remarkably high performance at predicting what action was taken. All right, so that was all about training the IDM. Let's move on to seeing how we train the VPT foundation model. Here you can see how well it works. Here you can see the data. As we across training time, you basically see that the model starts to learn zero shot to do kind of the simple things that humans do in the game. So breaking that down, it does things that humans do in 2 seconds, like all the time. A little bit less common, but still with some frequency. It does things that take human about 14 seconds, which is to collect logs and planks. And it even starts to do things like make crafting tables, which take humans almost a minute to do in the game, which is almost 1,000 actions. So normally, if I had more time, I'd show you a video here of the agent going off and producing a crafting table, but I'm not going to do that because I'm going to show a similar video later where it does even more complicated things. In addition to just doing kind of crafting table stuff, we found all these interesting behaviors that we didn't expect under the zero-shot model because we're just, like GPT, we're just training it to do what humans do. So it learns to hunt animals here, which requires tracking this animal and hitting it multiple times. It learns to swim and keep its head above water. It learns to eat food, and it even learns to do this Minecraft kind of specific behavior that humans do all the time in the game, which is pillar jumping, where you jump up and you put a block below you to produce, to a really, really tall pillar go up in the air. So that's just pre-training on kind of generic data off of the internet. Another thing we can do, which comes from the GPT playbook, is we can fine-tune via supervised learning, via behavioral cloning, but to a narrower data set. So we said, we're evaluating on the full, like we're training it to do things throughout the entire game, but really we want to see it do really well at the beginning of the game because that's what we're kind of evaluating it on. Our evaluations never get to the end of the game. So we ask contractors to do stuff that's very common to do in the beginning of the game, which is to go and build a house. And so we asked them to do that with basically simple materials. And then we fine-tuned to that kind of very small 400-hour small data set. And what we see is this massive lift in performance, sometimes as high as 200% in some of the things that it's doing, like making crafting tables. So a huge lift when you kind of do this fine tuning. And this is known for GPT too, where you basically get much better performance if you fine tune to say answering math questions or answering questions, just Q&A, than if you take the generic model trained on all internet data. So some of this, we also, with this fine-tuned thing, we start to see the first emergence of wooden tools and stone tools, which take humans over 2 minutes and like almost 3,000 actions to perform, which is pretty cool. So we're going to use this model, this early game model, this green model is our kind of basis when we go into RL training. One final thing to mention before we get to RL training is that it's not just the fine tuning to that small data set that's doing the heavy lifting. This is the effect of pre-training on the generic data set and then fine tuning on that data set across the amount of data you give to that pre-training phase. And what you see is you only start to get the emergence of the really impressive stuff when you've done a lot of pre-training on a lot of data, and then you do that final bit of fine tuning on the crafting table, on the house data set. Okay, so now we can also look at zero-shot behaviors that come out of this fine-tuned model. And there's some pretty cool stuff in here. So on the left is crafting a stone pickaxe. And you can see, just like a computer, it's kind of dragging and dropping and using that interface. In the middle, it's building a rudimentary house. And on the right, it's actually doing a really good job of exploring a village. It's entering houses, opening doors, opening chests, like kind of getting all sorts of loot, and et cetera. Pretty impressive. So another way that you can get a small data set to fine tune on is not by paying contractors to do something, but actually just doing keyword searches. So, we just search for things like Minecraft tutorial or like Minecraft basics. And we take the first couple minutes of that video and voila, now we have 3,000 hours of very, very, very early game data. And that is the green thing here versus the red, which was that's the red versus the green. And so basically you get roughly the same performance. It's kind of a cheaper way to get there. All right. They also, now I want to kind of switch to the original goal, which is we've got the pre-trained model. It should have a behavioral prior. It should know what it's doing. Now, can we fine tune it with reinforcement learning to go and do whatever we want? And can it solve hard exploration challenges? And so the task that we set for ourselves was trying to get a diamond pickaxe, which is a very, very difficult thing to do in this game. It takes humans over 20 minutes to do that and 24,000 actions, which is a remarkably complex thing for a reinforcement agent to learn to do. And you have to do all of these prerequisite skills to get all the way to that diamond pickaxe. And so what we did was we just reward basically every time it does any one of these stepping stones en route to this diamond pickaxe. And if you don't do pre-training, if you start from random initialization, the exact same model, exact same architecture, but just randomly initialized weights, no pre-training, it doesn't learn anything. It's basically stuck on the ground. It actually learns only the first stepping stone in that chain. Whereas if you use the VPT method, you do the pre-training first, and then you fine-tune with RL, then you get all the way to this diamond pickaxe. And we are fine-tuning from that model that we fine-tuned to BC. So it's actually a 3-phase thing. I'll recap that later. So the TLDR probably of the entire talk is this slide, which is that pre-training on noisy internet scale data works to solve really hard tasks and that are otherwise unsolvable effectively with vanilla RL. So it's also really cool to see that for every task except for the diamond pickaxe, we ended up at the human level performance in terms of success rate when challenged to go get one of these items. For diamond pickaxe, we're about an order of magnitude lower, but we just still saw it, at almost 2% of the time, which is pretty impressive. So here is the long video of the agent actually going and getting the diamond pickaxe. So the agent has to start off going and getting some wood. It opens up this little interface here, and now it has to start dragging and dropping little icons much as you would drag and drop icons if you were using Photoshop or like dragging files around on your computer. It requires a lot of kind of fine-grained dexterity and coordination and a knowledge of the interface. It does that. It then places this crafting table. Initially in their work, it would abandon the crafting table after it used it. But when we cranked Gamma up, it actually started planning for the future. So there it like takes the crafting table with it, it breaks it and brings it because it's going to use it here. So it's gathered some stone, it's going to place its crafting table, open that up. It's going to use that to make stone tools with this interface. Once again, it breaks down its crafting table so it can take it with it. It's now found iron ore, which it needs to make iron tools. In order to do that, it first has to harvest the iron. Then it has to place a crafting table because it needs to make a furnace to smelt the iron. So it makes the furnace, places the furnace, opens a totally different interface. It then places fuel under the iron ore to smelt the iron, waits for a while, grabs the iron, grabs its furnace and its crafting table. Actually, I think it left its crafting table. Oh, no, it went back and got it. All right, so now it's off to the races. It goes and it has to explore. Diamonds are really hard to find, so it's learned to explore. Explores this, here we go. It's found a little stash of diamonds. It breaks them all up. And then it will open its interface. Once again, it will place its crafting table, open it up, and then it will use the diamonds it has achieved that it could only have gotten with all of those tools to make a diamond pickaxe right there. So I think that's pretty cool. I think it's pretty impressive that it can do something that is so difficult and it's never been done before with reinforcement learning agents. So now I want to talk about adding language, which I'm super excited about and is a theme of this workshop. So text conditioning gives us all these really nice benefits. It gives us steerability. We can ask for specific things, and that enables zero-shot performance of new tasks. It gives us generalization via compositionality that allows flexibility, so we can ask for basically anything. And we've seen with things like GPT and DALL-E that this is a really, really good playbook. The language is very powerful. So our hypothesis is that we should get the same benefits for embodied agents if we train at massive scale on effectively action given not only pass, but pass plus text. And so the cool thing is that data is already there. So all of these YouTube videos, or many of them, you have a human that's doing narration while they're doing tasks, saying like, oh, first I need to go chop wood, and then I need to go, bring up my crafting window, and like you drag and drop these things in this particular order. And so you're getting this running commentary about what you're planning on doing in the future and how to do it. And so all we do is take those closed captions and add them as input to the model when it's trying to predict the next action. And then let's see what happens. And so this work is pretty preliminary. We started it toward the end of the project, right before I was leaving OpenAI, and we were wrapping the project up. We always had it on our roadmap, but it took us long enough to get the normal VPT to work. And so I think the sky's the limit, and like you could get this stuff to work way better. But here's what we did in a kind of a quick rush. We took 17,000 hours of videos that had these closed captions, text narration. We tuned a smaller model where we take in 30-second chunks, we run the text through OpenAI's API for GPT-style embeddings. We then run that through 2 layers that get learned, and that then goes into the normal architecture of the ResNet. It gets combined with division information and goes into the transformer to make the prediction. So we didn't do a lot of tuning here. I think we could get much better, but even the preliminary evidence is quite encouraging. So when you ask it to, for example, dig dirt or go build a house or get wood, it doesn't explore very much. But when you ask it to explore or go find water or seeds, which are usually far away, then you get much more distance traveled, statistically significantly more exploration. When you ask it to get seeds, you get seeds, or when you ask it to get wood, you get more wood versus asking it to do other things. And the same is true for dirt, where you also get digging if you ask it to go get dirt. So I do want to emphasize it didn't work in every case. These are kind of like the best cases that we saw. But I think with a lot more data work, tuning, et cetera, that this thing would really work quite well. So I want to share a couple analyses of things that we learned along the way. One thing that really mattered was that behavioral cloning fine-tuning step in the middle. So if you just go from the original foundation model where you did the entire data set one, not the one that's focused with that second step of behavioral cloning to the house building data set, It didn't work very well. We got this kind of flatlining performance here, but that kind of getting it unlocked and getting those skills dialed in really helped. I have a feeling that with more training and like more data, more compute, better optimization, you actually could not need that step in the middle. But if you're on a project and you need it, that's a nice option to have. Another thing that I think is really essential and important is that we needed a KL penalty during RL training to the foundation model. So we start in this case with the model that got fine-tuned with behavioral cloning. And if we don't do a KL, if we just start doing RL, you get this orange line here. So it learns a few things and then it stops learning anything else. But if you do the exact same model, but now you do a KL to the starting model, the model at time step 0 here, then you get this nice green curve. And why is that happening? Well, think about it. While you are learning to do the early stuff, you are not using the skills that you will later need in the Iron Age. And so you will catastrophically forget them while throwing all your resources at learning these early tasks. But if you do a KL to the original model while learning these early skills, you're basically preserving the information of the skills you will need later on in learning, such as like the skills that are necessary in the Iron Age. And then once you get to the Iron Age, those skills are still there to help you kind of learn the next rung in the skill ladder. All right, so data scaling, I want to quickly show you some things. I've showed you this plot before. It's kind of interesting to look at the effect of how much data you need to train an IDM in terms of the downstream performance on the behavioral cloning model. And one thing we noticed actually is we could have, if you look over here, performance doesn't really increase between about 100 hours of data and 2,000 hours of contractor data. And so we probably could have gotten by with this lower level of accuracy, which just means it's cheaper to get the original data you need for this process. Another thing we thought was pretty interesting is comparing what happens if you just do behavioral cloning on the data from contractors versus using that data to train an IDM to label noisy internet data and then train behavioral cloning at much greater scale. And that's what you see here. So focus on the right plot here. This is after fine tuning. What you see is you only start to get really complex skills like stone and iron tools if you are using the internet data. If you just use the contractor data and BC from it, you don't get a lot of performance in those things. In fact, you never see stone tools. Okay, a little bit of discussion before wrapping up here. So one thing I think is really interesting is we're all kind of, I think, probably sold on self-supervised learning if you can get it. It's a pretty good idea, we know that. But I think self-supervised learning usually gives you what I would call a representational prior. It helps you see and understand the world. Like if you did like pixel prediction or video prediction or something, then you might know that these are chests. You might not know the word for it, but you might know basically what they are, but you wouldn't know what to do when you see them. Because you just know how to see the world, right? You've just done pixel prediction. But the behavioral prior that comes from VPT tells you what to do in this situation. So instead of just knowing that these are chests, you know those are chests and I should go open them and how to open them. And so you don't have to learn that. So it's like a next level kind of leveling up via pre-training in terms of learning to act in the world versus learning to see and understand the world. Another cool idea that we had throughout the project actually was that we were hoping that we could train a general IDM in like a feature project that would not just work in Minecraft, but might work across different domains. We actually saw somebody take our Minecraft thing and have it watch some other game and was decent at making predictions. But this work from Venuto actually confirmed our kind of wildest dream, which is that you can actually train a general IDM. So this work followed up on VPT and showed you can kind of train a generic IDM. And then when you give it the next task, you only have to give it a little tiny bit of data on that next task, and you can quickly fine tune it to do well on that task, which is pretty cool. All right, so to conclude, VPT can learn to act directly from vast, noisy, unlabeled online video. It does that by learning a behavioral prior, which we think is likely much better than a representational prior. It would be cool to go do that as a specific study, compare it to other techniques that just give you the representational prior. We didn't do that, but my money's on the behavioral prior. We also think that, and have shown really, that VPT is much better than doing behavioral cloning if you have a small amount of data. It's much better to take that data, train an IDM, and then unlock the internet's data rather than just be seeing on that small amount of data, which is really cool if you think about it. You can take like $2,000 worth of contractor data and unlock the millions and millions of dollars of unlabeled data that's on the internet. That if you had to pay for that, pay contractors to produce it, would take something like millions or more of money. hundreds of millions. So another cool thing is that VPT can use the human interface directly, mouse, keyboard, and act at 20 hertz. And like GPT, it has really nice zero-shot behavior, but it also gets much, much better if you start fine-tuning it in a pretty simple and efficient way to take advantage of with small targeted data sets. So you can kind of turn that nice generic prior into something that really works well in a targeted situation that you care about. And finally, or not finally, but finally for this slide, the three-phase thing worked surprisingly well for us. Pre-training on generic data, then BC fine-tuning, so supervised learning, behavioral cloning to a narrow targeted data set, and then doing RL from that. That was the best combination for us. And then the final slide of conclusions is that I thought it was really interesting that this KL penalty to the original model helped maintain the skills that were necessary for later learning by combining catastrophic forgetting and allowing exploration to persist for a really long time, basically to protect that behavioral prior until you need it. We saw all the kind of classic things you see out of OpenAI papers in terms of scaling, helping data. More data helps, bigger models help, and longer training helps. And in the end, the most important result is it learned to do a very, very difficult task that takes skilled humans over 20 minutes on a computer. And I want to think about that. Like, I think this method will work very well for computer using agents that use any software on your computer. And just think of all the things that you can do on your computer in 20 minutes. If you had a virtual assistant that could do that, I would be pretty happy. And I bet a lot of people would as well. So that's kind of really exciting. And then the final thing I just think is tremendously exciting is combining this with text, where you can tell the agent what you want it to do, and other options that you can do with text that are super exciting. And we showed kind of with preliminary work that allows steerability, it allows you to zero shot, do some things that you weren't trained to do. And I think the sky's the limit in terms of creating open-ended algorithms that take advantage of that to go off and learn an arbitrarily large and growing set of interesting skills. So with that, I want to thank all of my collaborators on the project, this fantastic team of people you see listed here, the organizers for the invitation, the reviewers at NeurIPS, and all of you for listening. Thank you.